Yeah, so thank you very much for the introduction and the invitation. I would like to tell you something about our efforts when it comes to glass statics and making that a little bit more usable. So for those that actually have to use it. So this really holds true for windows and facades in the vertical space. So regular windows, no roofs, and also no specifically big special wishes. So nothing like that. And I would like to limit it to the 90% of all glass that is being used in construction. And oh, I'm going to need the device to move on to the next slide. That's quite helpful. Thank you. All right, so this is very provocative. That is glass, traditional glass. Glass can break with all the repercussions. We want it to be replaceable quite easily, no follow-up damage. That is the dimensioning concept. And then, of course, there are some rules that derive from that, how to deal with it. And it's just material glass. And of course, the building is like that. So it's about half a square meter at most. And for a long time was fine until glass got really cheap and all of a sudden there were application in spaces that really don't have anything to do with how glass was used in the past. So the picture right here, that's the forum at the airport. And if you want to see glass applications, everything is there. So from the roof to anything, really. And that not being a good match without any rules and without any dimensioning is obvious. And when it comes to this engineering and the dimensioning, there was lots of criticism. And to summarize it briefly, everything was way too much work, way too complicated. And I had to agree with it. So if you think about a window in buildings, of course, I can't agree if you look at the airport in Munich. So how do we handle this situation? And if we talk about applications, if we think about the fair in Leipzig, which is one of the biggest glass roofs back then also the Munich airport. There's this white and red band that was used for it, and then also accessible staircases that are already broken and horizontal glass that fell over. And of course, we need rules for that, and Europeans tried really hard for those. I just wrote down 1987 to 2004. That's when they wanted to introduce the first norm that Germans didn't like at all. And ever since then, on a European level, so we also need approval and we need rules. And there was also a series of different rules. And most of the time, they're technical rules X. And the X is then line shaped and for fall proof glass and many other things. So one thing is for sure, if it breaks, it needs to break in a safe way. And the term safety, and that is what we heard in the previous presentation, that is something that you always have to see in the context of the risk evaluation. And a lot of people want some clarity and they want really strict rules, and we know exactly what to do. And then also the contrary opinion, who's supposed to pay for it? Does it even make sense? So this is really the area we're in. And I would just like to tell you about the basis. So we always tried, even if maybe it was rightfully done, but we always tried to consider this criticism as well. And even in this first rule, the technical rule for the line-shaped glass, that is something that was much easier in terms of showing proof, which made it where solutions for regular glass windows were given. And of course, the Institute for Window Technology published some application protocols that actually looked like they do now. So it's sort of the same or similar diagrams that I would like to introduce today. And with that, these complicated calculations should be avoided, and everything that is bright in here is allowed, everything that is dark is forbidden. And I hope I have this laser pointer here. Does it work? Probably not. I don't know if you can see it, but these areas right here, these two edged size spaces that are 1 meter big, that's still climate burden. That's how they're known today. And of course, that is because of pressure differences between the space in between the windows, and then also because of changes in air and things like that. And we said that for normal windows, we're just gonna not need diagrams like that. So we should use regular glass for windows, and you have 1 meter 60 1 meter 60 space, and there are also some other circumstances that are to be considered, but the actual size was 1.6 square meters, and everything below that is okay. So overall, I would say that definitely contributed to peace, because 89 or 90% of all windows were covered, and for facades and things like that, it just was accepted that you had to use a different solution. Okay, so this proof then actually was also you put part of the 2010 edition of the norm, and with that, everything else was as it always was. And in the 2020 edition, there was some criticism that they talked about, and I would like to mention that as well, because that led to actually having an AGB. So what is it all about? This simplification of this proof is very pragmatic and science-based. So it is something that there's no good reason for, specifically for small formats. So the question was always as, okay, why can I use that? I think it's very difficult to disprove, but we have found a solution. So the repercussions of the damage is now in the basic norm for dimensioning. So it's defined. So if we actually have to show proof for carrying capacity and what we do with it, and if we talk about carrying capacity, it would be 1990. So it would be that there's failure of carrying capacity. So the whole building would collapse, as it was the case in East Asia before. So an 8-story building just collapsing and a couple thousand people being in there. So this would be failure of carrying capacity. Of course, that could also be the case in different scenarios that has happened before. So bridges, for example, think about Genoa. It was a highway bridge that just collapsed. And of course, that's what you don't want. And that's why there is a likelihood of 1 to 1 million set as a basis for all of these statistic calculations that are in the background. So just remember 1 in 1 million. So if you think about that, 1 in 1 million windows being broken, then I think it'd just be too much for private buildings. And that's exactly what we see here in this norm. So the differentiation of reliability. So that means that we actually are asked, not we can, but we are asked to take measures to optimize whatever that means in this context. So it's just an optimization considering the repercussions of damage in order to actually keep building costs at our acceptable level. That is sort of contradicting what we heard earlier, and of course, we're also asked to think costs. So, of course, they need to be appropriate in line with the measures. That's not easy, that's clear. And of course, there are some things that are up for debate, but we are asked to do that. Okay, so let's try to do that as best as we can. There is a risk analysis, and when it comes to small glass pieces, I'm gonna have to do a risk analysis, and of course, you can make some assumptions. And in the association, we agreed that when it comes to small sizes, what is small though? So they just decided that it's 2 square meters. So 2 square meters or smaller, which be small pieces. You just actually need to have the carrying capacity test. So that means talking about likelihood again, 1 in 1,000 glasses can break within 50 years. So that's the breaking risk by a factor 2,000. That's how much it's been increased. So from 1,000,000 to 1 in 1,000. And for that, they also sort of have a rule as to how to prove that. So I have the BF rule. So there is a publication that was published. This is where the diagram came from. And it is incredibly complicated, as you can see. And that also means that the point that you have, well, nobody can calculate that anymore. We are all using programs anyways. So if we do use programs, it doesn't matter if it's complicated because nobody needs to understand how it works. The most important thing is that they actually hit the right button on their computer. So me being a scientist, I think that is a catastrophe if I don't even know what I'm doing anymore. So of course I can still use the computer, but I don't know what the computer is doing. But of course, that is even worse in other things when you use artificial intelligence, for example. Of course, that is sort of a buzzword at the moment in many areas. And when it comes to artificial intelligence, you don't even know why the computer is doing it. You just know that it is doing it with our programs that we're using right here, these universal glass statics programs. It's still a program that was developed by a programmer that knew what he was doing. And of course, we don't always want to use the computer and just type in all kinds of information, but instead it should be simplified. And the answer is yes, it can be simplified. We can actually use the application diagrams again. And that was also the project that was here bei the Glaserhandwerk and also IFT as well as Tischler Schreiner and VFF. They actually started with it, and it is our goal to actually have a type static test for these glasses, and based it needs to be based on this risk analysis that is published in the 2020 edition. So the new edition of the 18008. The problem is that this 2020 edition is not introduced legally, and because of that, it can't be the basis of a type statistic, statics analysis. And that's why we thought about, okay, how can we follow that up even more? Number one would be to just wait until it is legally introduced in Germany, or at least in one state in Germany, then we could have applied for it. But that was a big question mark. That's why we said that we are going to ask for official approval by DV, and then we can use that. So the application area was established quite quickly. However, that has now increased to 40 different insulated glass units. So with 2 glasses, with 3 VSG, ESG, and the size could be 3 times 5 meters. And then the application area would also have to be limited, and I already mentioned that. So if you also need to have a fall-proof glass or ceiling glass, for example, roofed glass, then of course it'd be super duper complex. And we thought as a first step, we are going to use 90% of the application cases, so that we vertical glasses. So the size of the building would be up to 18 meters. And it now turned out that you could even go up to 25 meters. And it should definitely also be possible on the edge of the building. Experts probably know that the edge of the building is difficult because there are increased tensile loads, and that should be considered. And then, in the context of this, there was a second question that came up, and that was that the temperature should be determined more specifically. In the past, temperature and pressure at the end of the last decade that happened, so in 1995 roughly, and they actually set some values that were on the safe side. And of course, there were some simplifications that were already approved for that. And the question was, can't we be more specific? The answer is yes. And of course, that can also be done in the context of this approval that can be covering everything. And now, what does it look like? It has a very nice number. There are two things in there. So that would be type approval. So it's in line with 18008 Part 1 from 2020. So it's the new version. That was the basis of everything. And the second thing is that the modification, like tensile load, for example, that is something that experts know about. And if not, then of course we are very much more specific. We are more on the safe side with that. So if we do that, we can actually look into these diagrams. Unfortunately, I don't have a clock right here, so I don't know how much time I have left. Okay. All right. So I can continue with that. You may be familiar with that. That's how I really started. So this is the wind load level. It's a different format. And these diagrams always have some zones, forbidden zones and allowed zones. In this case, the bright color, the white color is the zone that is allowed. And we have the short edge to the top, that's the y-axis basically, that's up to 3 meters. And then the long edge would be up to 5 meters. Up here, it would be what kind of glass it is. So for everyone, we need to have an individual diagram. And then we also have the wind load level. So in this case, it'd be wind load level 3. And an example, so we have one glass, 110 by 230. 110 would be the shorter edge, and the longer edge would be 230. So we're going to end up at OK. So the glass can be proven to be used. So this is how quickly statics can be done. It doesn't even take 5 seconds if you actually have the right diagram on the right page. And you may need a couple seconds extra because you're going to have to determine the wind load before, but I'm going to talk about that later. Okay, so now we're going to simplify everything. Oh, now let's look at what we have up here. So if you have a bigger glass, 160 by 230, then you're going to end up here in this red area. So that means that the glass is going to break because of wind. And if you're under it, then it's because of the climate load. Okay, so we're going to leave the top part out of this diagram, and we just assumed that it has 4 sides, so overall that is included. So if there are 4 sides to it, then the sides are interchangeable, so this diagram does need the top part. That makes it a little bit easier, and you can also read it more easily, and the shorter edge is always shorter than the longer one. So some people call the next thing a trick. So statics have improved, so static calculations have changed. And if it comes to 4 sides, we have up to 1 to 2 size, we have an effect that's very helpful, and that's the membrane load-bearing capacity. So this red area is now white all of a sudden, and the point is then changing from red to green. So now you can actually do it. And now we have G, risk analysis for everything under 2 square meters, and that makes it where what you see here is going to turn green because if you're below 160, it's okay. So now we have the membrane load-bearing capacity first, and the risk analysis for small ones as well. So now this is what the diagram looks like, and the bigger one is now green, and the lower one because of the risk analysis. So I think now we're at an area that you can talk about. This is for wind load capacity 3. So this is point 0.8. So in regular buildings, this is actually the regular wind burden. You don't have a lot of wind if it's just one level. So you could also use bigger glasses. It could be 16 meters. So it could be less than you can use. So of course, all of this can be 3 in 1. Or if you have 5 wind load steps, you could also use those. And then the diagram looks a lot more interesting. And it's also a bit more colorful, so it looks nice. One thing that stands out is that this part down here, that is not changing at all. So that means the climate burden is independent of the wind load. And of course, we can't get away from that. It's going to stay like that. And that also means that the wind in and of itself, for the top parts, 1, 2, 3, 4, 5, how do I determine the wind? That's very difficult to do. So we have a new norm, 1991-14, that says that the wind is calculated by pressure, speed pressure, and that depends on the location. So whether you are in northern Germany or in Frankfurt or in Nuremberg, and then it also depends on what the building looks like and where it is in the building. So that would be A, B, C, and D, and there are tables for it. And I would say it's an independent thing. A colleague in Rosenheim. So wind would be one of the main things. Let's do it very simply. We are going to use these buildings right here. That's what we usually have. So we're going to use up to 18 meters, and then it can be simplified. And we have 3 things that we need. So number 1 would be where am I? So it'd be 4 wind zones in Germany. It'd be wind zone 1. Nuremberg is part of that. Then we have wind zone 2, wind zone 3. That's closer to the coast. And then the coast itself is only 5 kilometers wide. So if you see water from your house, you're by the coast. We left out the coast in and of itself. We still have to calculate that. And I would say everything other than that requires a program. So we have 5 wind load zones. We need to know the location. We need to know the height of the building, which is very important. We have 2 differentiation facts, so 5 to 10 meters and up to 18 meters. And we need to know where we are. Are we by the edge of the building or not? If we have all of that, we can determine which wind zone we're in. I think that is still great. And with the climate loads, I mean, they're super complicated anyways. So we just use whatever's in the norm as our standard values. So if we do all of that, we're going to have these great programs. So I don't know if the associations came to a conclusion whether or not they wanted in color or black and white, but the content is the same. As an example, I'm in wind load stage 5, that would be wind zone 2, Berlin, for example. So below 18 meters. And unfortunately, the building is by the or the window is by the building edge, then you're in wind zone 5, so it's 120 by 3 meters. The green dot shows us where we're at. Is it approved in wind zone 5? Yes. So if you're below line 5, it's acceptable. So if you're in the middle of the wall, you're in wind load zone 3 and you could 150 by 450. So that would be maximum capacity. What you can't do is having half a meter by 450. That is going to happen very rarely. If these diagrams are too complicated, you could also do maximum measurements. So for load zone 5, we're going to have the maximum of 130 by 260. Or zone 3 would be 170 by 320. It's still up for discussion whether or not you're going to do something like that, but of course, it also exists in other editions. So if you use VSG, for example, 6 millimeters, simple glass, F4 in the middle, and then 8 VSG, then of course, you have 2 times 270, or a bigger one would also work, and then 0.8, so 80 centimeters by 3 meters wouldn't work. That's red. But if you really, really need it, then you could use the 6 millimeter float glass, the one up here, and you could replace it with an ESG, and then everything is going to work again. And with that, I'm at the end of my presentation, and I hope that I convinced you that this is a great tool in order to have more safety. And of course, this is also a great overview. We're doing great. Well, we have 40 diagrams overall. I was very optimistic. So they're going to be finished in 2022, so this year. And I would also like to say these diagrams are great, I think. But of course, the user also needs to use their own mind. That is required. All right, that was it. Thank you very much.